you to this series of lectures on PTL on marine hydrodynamics. In the last class, we have talked about gravity wave maker problem. Basically, we have talked about the Havelock's expansion formula, and today we will just see a similar one application of the Havelock's expansion formula, that is what the reflection gravity wave reflection by a wall. Basically, we consider here a vertical wall. Suppose I say that I have a wall here. Suppose I say I have a wall here, I have a vertical wall, and I say that I have a wave which is propagating and it hits the wall. So, if I say this is my incident wave, there is an incident wave, I call this eta I is a e to the power a I e to the power I times k x minus omega t. Suppose this wave, when it hit the wall, there will be we all know there will be a reflected wave, and that reflected wave I call it AR e to the power I times minus I times I k x minus I omega t. Then here what we are looking at as an application of the expansion formula developed in the last class, I will see how what will be happen to K R, that is A I by A R, and that is what I mean the reflection coefficient. When a wave basically, so here what we want to study, that when a wave, and I call this as a wave reflection by a vertical wall, rather call it a gravity wave reflection by a wall, by a vertical wall. So, here I am interested in knowing what is K R A I, sorry, A R by A I. Basically, this is the amplitude of the reflected wave to the amplitude of it is the ratio of the amplitude of the reflected wave to the amplitude of the incident wave. This is I. So, this is basically A R by A I. So, now what we will do here, if I look at the, I will take the problem in this way. So, we have a wave, we have a wall here. So, here I have what has happened here, I have del square phi 0 in the fluid region, and I have as usual phi t t plus g phi by 0 on the free surface, that is on the mean free surface, y is equal to 0. And here I have a vertical wall, on the vertical wall I will have normal velocity 0, so phi x is 0, and this suppose the wall is located at x is equal to 0, and then if I just say that my water is of depth, finite depth, suppose y is equal to minus h is the bottom surface, then I will have del phi by del y 0 here on the bottom. So, this becomes my mathematical problem. So, I have to know what is phi, and I have been given that eta is the incident wave and eta r is the reflected wave. So, in the process that will give me that what happened at the far field, this information provide me what will happen to phi at the far field, that will it will behave like, from this relation of eta I, it will be A g by I omega, A g by I omega cos hyperbolic k naught into h plus y divided by cos hyperbolic k naught h, and that will be, sorry, A I will not, I will take A I e to the power I k naught x minus omega t plus A r e to the minus I k naught x minus I omega t. So, this will be the behavior as x tends to minus infinity, because this side is x is 0. So, this wave is coming from minus infinity initially, like this wave is coming from incident wave is coming from minus infinity, and it get reflected. So, this is this A I is associated, rather A I here, if I look at this, A I is nothing but the wave, that is amplitude of the wave that is associated with the incident wave, and this is the amplitude, A R is the amplitude of the wave that is associated with the reflected wave, and since eta is this, eta r is this, so my phi is of this form, and as we have seen that this is in a boundary value problem of this type where infinite domain, this also sometimes called as the infinity condition or the radiation condition. The condition at infinity is called sometimes condition at infinity or the radiation condition. Often we call this as the radiation condition. So, this condition is called the radiation condition. Now, with this if I now, like in the previous class what we did, if I just like the previous class, if I have the full expansion of the potential, what it will give me, my phi will be, it will be I g rather g by I omega cos hyperbolic k cos hyperbolic k naught into h plus y divided by cos hyperbolic k naught h into this is not a, this is g by omega into this is a I e to the power minus plus I k naught x plus a r e to the power minus I k naught x into minus I omega t plus, because as I have seen in the expansion formula last time, I have seen this is n is equal to 1 to infinity, because there will be a local effect which we call the Evansen modes, and this also satisfy, and that form will be give us, I call this as a n e to the power minus k n x cos k n into h plus y divided by cos k n h, and that is what into e to the power minus I omega t. We can see that if I look at the radiation condition, then as x tends to infinity, this will be a plus sign, and this is as x tends to infinity, x tends to minus infinity, what will happen? This term will contribute to 0, because e to the power of x is negative, x tends to minus infinity. So, this term will tend to 0. So, all these terms will contribute to 0, and in the process this part remains the wave part. So, these are called the, this part of the solution what I call the local effect or the Evansen mode. This is all the Evansen modes, and these are the progressive wave solution of this. So, basically this represents the wave part that is propagated in the x direction, and this represents the local effect. So, in this sense, now if I will say that I have another condition which is say that my del phi by, because there is no near the wall is a vertical wall, and there it is del phi by del x is 0 at x is equal to 0. If I have this, then what it gives me? That gives me, so like the previous case, if I take this will give me I k naught, which implies I k naught into a I minus a r, and I call this as this term, or there is a I g by omega, g by I omega here also, and then I just call it I k naught into a I minus a r. I call this term as my f 0, like I have done in the previous case. This I call this f 0 y, and then I call this term my f n y. So, if I say, then what will happen? I k naught a 0 minus a r into f 0 y, then plus here I will get k n, then a n f n y, that will give me 0. So, if this is the case, and then I know I have already seen that in the last class we have already talked that minus h to 0 f 0 f m f n f m y into f n y dy is equal to 0, m is not equal to n, whether m n 0 1 2. This I have seen it last time, we have shown this while deriving the Havelock's formula, and once you will utilize this result and substitute here. So, what we will do, we will integrate with multiply with f 0 and then integrate over minus h to 0 like this, and that will give us, if I apply this basically. So, if I apply this relation, this relation if I apply, what it will give me? That will give me a I minus a r is 0 and a n is 0, because first time you do the f 0 multiplication, first multiply with f 0 the expression, and then you will see that the first term f 0 is non-zero, where f 0 f n is 0. So, that will give the this term, and then again you multiply with some m f m y, and then you do the integration for all minus s to 0 for m is equal to 1 to infinity, then you will see that m is 0 in all the cases, because right side is 0 and once is 0. So, that means a I minus a r is 0, that gives me r k r, and which implies a I is equal to a r, which implies k r is a r by a I modulus, and that gives me 1. On the other hand, what happens when all a n is 0 for all n equal to 1 to this thing. So, my phi becomes I g by omega or g by I omega into cos hyperbolic k naught into h plus y by cos hyperbolic k naught h into, I can call this a I, I will take a I common, rather call it a I g into e to the power plus I k naught x plus e to the minus I k naught x into e to the minus I omega t, and that is what. So, here I am getting what I am getting here, that in the process, because the Evanston modes all n's are 0, am's are 0. So, the Evanston mode does not contribute. So, a local effect becomes, there is no contribution from the local effect, only the progressive wave solution remains. And if I look at this phi, then what will happen to my corresponding eta? And in this case also I saw that k r is 1, that means all the waves that is incident on the wall get reflected. So, that shows that in case of a vertical wall, if a progressive vertical wall, when a progressive wave is incident, 100% reflection takes place if the wall is vertical. That means there is no dissipation of energy, there is no energy loss or gain of energy, and all the energy, that is all the wave energy that hit the wall get reflected back. That is, and in practice it is always, it has been found that 97 near a vertical wall 97% of wave energy get reflected, another 3% may be converted to sound and other energy. But if we are, since in the context of this analysis on the linearized theory, we are also finding that 100% energy get reflected, 100% wave energy get reflected back. Now, here I have a question comes, what happened, because when a here 100%, but if you look at the corresponding eta, because we have a eta which is a ai is a ar. So, I will call it ai into e to the power I k x minus omega t plus into the minus I k x minus I omega t. So, that will give me ai e to the power I omega t and e to the power I k x plus eta minus I k x, that will give you 2 cos k x. And if you look at the real part of eta, that gives me 2 ai, this is cos k x into cos omega t, and that is what is the amplitude of this superposition of the waves. That means, when the initially the wave that was hitting the wall is eta I is a I e to the power I k x minus omega t, or the real part of this, if you look at the real part of eta I, that is some a I, because I am looking at the real part into cos k x minus omega t. So, and then the resultant wave is of this nature, because this I can assume that this is a real number. So, here also AI, as if I consider AI as real, then this can be also a real number. So, no problem. So, that means if I have a wave which was a progressive wave, when it hit a wall, the resultant wave is this on a vertical wall, and this is same as this, and that is shows that the resultant wave is a standing wave. So, standing wave, and I have talked about standing wave much before in the early stages, but here we have seen also that a standing wave is generated, particularly in case of a vertical wall, no energy no local effect is becomes negligible, and there is no loss of energy, or no energy is converted to energy does not get converted to other forms of energy. So, all the ways, and then here the amplitude of this wave is twice the amplitude of the incident wave. So, this is what we learn from this example, and in fact, this expansion formula of Havelock, this is one of the simplest example to show how Havelock's expansion formula can be applied to wave propagation problem near a vertical wall, and the same concept is used to apply to vertical structures of basically flexible porous structures, and also to sea walls or breakwaters, and any, in fact, in offshore engineering also for calculating the wave load on a structure and many other applications. So, that is what we do here, and upon this approach is called the theory of refraction. Now, this approach I call this this is just, in fact, this approach is a straightforward approach basically to obtain the total velocity potential phi associated with the flow problem. And once we know the total velocity potential phi, then we can easily know what is the pressure that is acting on a wall, and once we know, because pressure we know P is rho phi t plus zeta, phi t plus zeta, that is called the pressure, and once we know the pressure at any point, so we can again calculate the force. This I call the pressure P will be this, and then you can calculate the force on the wall by integrating the pressure over the surface area, and that will give us the force. So, wave load on a wall can be easily calculated. So, in fact, this concept is used in various cases. Sometimes this concept of wave scattering or wave diffraction is used to calculate the wave load on many structures, particularly large offshore structures where the wave amplitude or wavelength is much smaller than the size of the structure. So, this is this method of this is although a simple example, but using this expansion formula of Havelock, we can also calculate the wave load on a structure, basically the wave force. When I say wave load, it is basically wave force. Initially, we obtain what is the scattered potential, what is the refracted potential, and what is the local effect, and after knowing the local effects and all these individual terms in the expansion formula, in that case depending on the nature of the boundary condition, we always get phi, and once we know phi, we find the pressure and then find the force. Upon this is called the, for wave load calculation, this is called the theory of diffraction, method of diffraction. So, this is I will come to that maybe in the next class or later. So, with this I will just talk about, because we have given the two examples, one is the expansion formula and then this wave reflection by a wall, to understand what happens exactly when a wave, how to calculate the total potential. Now, so knowing this reflection and the scattering problem, or the reflection and the wave maker problem, now I will go to look into a scattering problem. So, what happens in case of a scattering problem, because these two last lecture, this lecture, it talks about how the wave propagation takes place and what are the two processes. One is the reflection we have talked today, and now I will talk about the scattering. In case of a scattering, what happens, as I might have mentioned this, that suppose I have any structure, whether it is a submerged one, whether it is a floating one, any structure. What happens here, I have a wave which is incident on the structure, incident wave, and there is a wave which is a reflected wave, and then we have a wave which is the transmitted wave. So, three things here. eta I is the incident wave, eta r is the reflected wave, and finally eta t is the transmitted wave. Once we have this, and here what happen, my eta becomes eta I plus eta r on the left side as extends to infinity minus infinity, and eta is equal to eta t as extends to close infinity. So, and plus this is the radiation behavior, and then we will have the local effects, associated local effect. So, that is why, and this is the process. In this, suppose we know the nature of the structure, if we know the nature of the structure and assuming the structure is known, then how much wave energy get reflected and how much wave energy get transmitted when a non-wave of amplitude non-wave eta I hit the structure. That is what we do in case of a scattering problem. Now, today I will discuss a very simple example of a wave transformation, basically how the, here I basically I will concentrate on the scattering of waves due to change in the bottom geometry, and that will give us, and then relate the same with the energy relation. So, what we will do here, suppose to do this I will just look at one of the aspect of the problem is, that is I will consider, let me say that as if I will talk of wave transformation. Wave transformation over inhomogeneous bottom bed. Over inhomogeneous bottom bed and wave energy relation, how they are related. Okay. So, to do that we all know that if eta is a e to the power I times k x minus omega t, the corresponding phi is a g by omega I omega rather into cos hyperbolic k h plus by I cos hyperbolic k h into e to the power I times k x minus omega t. This is all we know. Now, suppose I have a wave, and this wave propagate over a depth, okay, let us say that from depth of water h 1 to a depth of water h 2. Then what will happen when this wave, and this is the point of line of demarcation, because this is where the depth abrupt changes in the water depth. And let me say that I consider only wave reflection, takes place. This is only, I only consider the wave reflection process, only reflection of waves takes place due to the wall. So, in that case what will happen? So, basically I will have two things, wave will be reflected, one wave will be hit coming, and because I have a change in the topography. So, a part of the wave energy will be reflected, another part will be transmitted to the other side. So, this will be also, this problem will be also can be called as a scattering problem. It is referred to as a, rather we call this wave scattering. This is a wave scattering problem. So, in this case what will happen? So, I will have my eta I, and eta will be a I e to the power I times k x minus omega t, and I will have also eta r, that will be a r e to the power minus I k x minus I omega t, and I will have my eta t I will have my eta t, that is a t e to the power I times k x minus omega t. So, if these are the things, then what will happen here? If these are the incident wave, this is the reflected wave, and this is the transmitted wave, then what happens in this case? Then what will be the corresponding phi? So, and in this case my eta on the left side will be eta I plus eta r as extends to minus infinity, because this is the wave which will propagate to the far field far end on the x side, on the negative side, and the eta will be that I call it as eta will be eta t as x tends to plus infinity. So, if I just say that the wave is my wave is propagating from here, and the wave that will propagate to the far field is again this is eta I, this is eta r, and this is the eta t, that is what the wave will be. So, here I am only considering these things. So, now, if this is the case, then what will be the corresponding phi at phi far field? That will be again omega by I g, this will be cos hyperbolic k, and this left side I call it k 1 because there is a change in depth, I call it k 1 into s plus y by cos hyperbolic k 1 h into a I e to the power I k x I k 1 x minus I omega t plus a r e to the power minus I k 1 x minus I omega t. Let me clarify here one thing is that why I call it k 1, because in all these things, because here there is a depth change, this water depth, initial water depth is h, I call it h 1, and in the initially this was in water depth, there is a abrupt change in water depth, and then the new water depth is h 2, because we all know that omega square is g k, tan hyperbolic k h, they will satisfy in both the regions. Even if for the same wave, the frequency of the waves remains the same, when the h changes from h 1 to h 2, k will change from k 1 to k 2. So, k 1 refers to the wave number associated with the water depth h 1, k 2 refers to the wave number associated with the water depth h 2. So, because of this, even if same wave frequency remains the same, when the wave propagate from the deep water from depth h 1 to depth h 2, the wave number changes, and this already I have talked about in some of my earlier lecture on waves. So, this is the wave which is propagated to the potential associated with this one, that is as x tends to minus infinity. Similarly, what will happen to the potential which will be, this is basically the condition at infinity, what we say sometimes omega by I g into cos hyperbolic k 1 into h plus y, and this will be k 2, because the right side is, as I have told, that k 2, this is h 1, this is h 2. Cos hyperbolic k 1 h 1, k 2 h 2, and this will be again a t into the I k 2 x minus I omega t. So, this symbol is very, because k 1 is associated with h 1, k 2 is associated. So, this will be the potential far field behavior on the left hand, this is the far field behavior at the right hand. So, now if I apply the energy relation to this, what is the energy flux? Laws from law of conservation of energy flux, we have, I have already told you, E c g is constant, the total energy flux is constant, wave energy flux that passes through anywhere. So, that means the wave that will be, if you calculate the energy per unit area or unit length here, is same as the wave if I calculate at this end, energy flux will be same. So, that way I can call it E 1 c g 1 is same as E 2 c g 2, and what is E 1? C g 1 is the group velocity of the wave that propagated from this end, C g 2 is the group velocity of wave that propagated here, and E 1 is the energy that is associated here. But on the left hand, this E 1 is a combination of two waves, one is the incident wave potential, one is the reflected wave potential, and both are in the opposite direction. So, because of that, what will happen? The same equation, what it will lead to, E times is rho g by 8 into a I square minus a r square, because this energy initially the incident wave energy is propagating in the positive direction, the reflected wave energy is propagating in the negative direction. So, because of the change in direction, the speed of propagation will change, and then the process, this negative sign comes to the energy calculation, and into rho g E into c g I call it Cg1 is same as rho g by 8 into AT square into Cg2. And if I put in the terms of rho g by 8 cancel, because these are same constant, and if that is the same constant, then we will have, I call it 1 minus AR by AI square into Cg1 is same as AT by AI square Cg2, and that gives me 1 minus Kr square is equal to Cg2 by Cg1 into Kt square. So, and what is Kr? Kr is AR by AI, and this is, and Kt is AT by AI. This is the amplitude of the reflected wave to the amplitude of the incident wave. This is amplitude of the transmitted wave to the amplitude of this, and this is what we call this, they are the reflection coefficient, and this is the general relation for the wave when a wave propagates from the far field. Now, here I have one more thing I want to highlight here, that when the wave propagates, suppose I have a wave, this is one of the very interesting. Suppose I have a wave which propagates from this, there are various changes in the water depth, and my final water depth is this. Or it can happen that I have initially the water depth was some h1, and this wave that there is a bottom changes, arbitrary changes, but at the end the water changes, it changes to a depth of h2. Because I calculate the energy flux at this end, I calculate the energy flux this end, because at any point of time there is a wave is reflected and transmitted, and finally the energy calculated at this end, and here the energy calculated at the same amount of wave energy. If there is only wave reflection is taking place, nothing is happening, then the amount of energy that will be going through this, because there is no loss of energy we are taking into account. So, same amount of energy, the energy flux, because same any cross section we think of, the total energy will be the remain the same. So, the energy that is calculated here is same as the energy that is calculated here, and in the process all these differences, it will not matter to the, only it will, the relation for this Kr Kt will remain the same, and all depends, this relation will set, but what will happen from case to case, the result for Kr and Kt will change. This result will vary, which will depend on the variation in the water depth. On the other hand, the Kr square plus 1 minus Kr square is Cg2 by Cg1 into Kt square, this relation will remain the same. Of course, Cg1 and Cg2 will depend again on the type of wave that is propagating, because here the depth is h1, here the depth is h2, and that will depend on that, and Kr Kt will depend on how the wave, what kind of disturbances is there in the local region. These are the far field region, in the local region, whatever kind of changes, and not only it is for this result will hold good for changes in the bottom topography, it will also hold good. Suppose I have any arbitrary structure which is there, whether a process of wave reflection. In the process of wave reflection, if I am dealing with just a scattering problem where wave is reflected and wave is transmitted, or you may have a bottom like you have a block, or you may have a trench, some such things, anything is there, you may have a floating body, anything, if it is related to the scattering of waves, and in all the cases this relation will remain, that Kr Kt relation what we have obtained, it will be satisfied, because these are all the local effects. Maybe the body is floating here, because wave will pass through this, and this will transmit to the other side to this. So, in all the cases the energy relation will be satisfied, and it is of this nature. Now, I will just go from case to case, that to say that how the energy relation helps us. Now, what will happen if I say Cg, Cg is nothing but C by 2 into 1 plus 2 kh, we know this, I have already find this relation, if Cg is this. So, what will happen in case of a deep water? in case of a deep water, we have C g is a C by 2. So, whatever disturbance is there in the local region, suppose I have a structure like this, or I may have a breakwater like this, or I may have whatever I have, any disturbances here, if C g is C by 2, then C g 1 is same as C g 2, because if both deep water case wave propagating from deep water region to deep water region, then C g 1 will remain as C g 2 is remain as C by 2, and if this is C g is C by 2, then we have 1 minus k r square is equal to k t square. This relation is again further simplified. So, that is in case of deep water, when a body is submerged somewhere. This is the wave which is incident wave, that is a reflected wave, far field behavior on the left hand, and there is a far field behavior, that is incident wave is there, transmitted wave is there, local effect will be there here. So, the local effect will not, it may be noted that the local effect will not, what the Evanston mode, they are not contributing to the generation, to the energy relation, only the far field behavior which is contributing to the energy relation, because the AR, KR and KT, these are the relation, the values of KR and KT is depending only on the amplitude of the incident wave and the amplitude of the reflected wave. Because of this, the however, although in simple cases like wave reflection by a wall, these quantities, all these Evanston mode contribution comes to 0, but it is not always true that Evanston modes they will not contribute, they will contribute to the problem. However, the energy relation only will depend on the behavior of K R K T, and in fact, if there are situations which arise, this is one of the very important relation. In fact, it comes in most of the wave scattering problem, because if it is, it may happen that you have, because this is like in case of a deep water, you are telling that K r square plus K T square is 1. If I say in case of it is 1, can there be K r square plus K T square, can it be greater than 1? If it is greater than 1, that means energy is added to the system, but there is no mechanism by which energy is added to the system. So, this is ruled out. On the other hand, if K r square plus K T square is less than 1, then what happen? As if there is a loss of energy, energy loss is taking place. In fact, this energy loss is a factor sometimes of evaluation of computation, because what happens when a wave passed a porous structure, there can be a phenomena of wave energy loss, and that is due to energy dissipation. Wave passed porous structure, wave dissipation takes place. And in the process there is a energy loss. Often it is very important, in many situations people are interested by a particular structure, how much energy loss is taking place. In fact, sometimes we use flexible structures. When you use flexible structures, floating structures, then often we say that the wave deformation, the wave energy loss takes place due to, because the energy, some amount of wave energy converted to deform the structure, and in the process deform the structure, in which wave energy loss takes place. Wave energy, it is not a loss in this case, it is energy transformed from the wave energy is converted to deforming the structure, and in the process we feel that there is a reduction in the energy propagation, both in the transmission and reflection. In such cases, this situation can happen, that K r square plus K T square is less than 1. Otherwise, because there these two phenomena, here energy losses takes place, here deformation takes place. By the wave action, mechanical energy is generated which deform the structure. So, in that process wave energy conversion takes place from one form to another, and in the process, because in all these processes, and this gives us a quantitative study analysis of the reflective, or talks about the reflective characteristics of a structure. Or dissipative or reflective characteristics of a structure. So, calculating this reflection and transmission coefficient, why these quantities, this K r and K T are important, and apart from K r and K T, this relation is very important, because it gives us lot of information without going to the detailed computation. If we know K r K T, we get all these characteristics of the structure, and it is because of this reason in various branches of wave propagation problem, this first people calculate, researchers first calculate the reflection and transmission coefficient, and they check whether these relations are satisfied. If this is satisfied, there is no energy, all the energies they are intact, only it is transformed from one form to another, whether reflected wave and transmitted wave, how much wave energy is reflected, how much wave energy is transmitted. On the other hand, if we had, when we think of wave past a porous structure, or there is a energy dissipation which takes place when the wave pass the porous structure, or in case of a flexible structure, the structure deform. So, there is a, so in that case, in these two cases this may happen, this has to happen, because there is a loss of energy or energy conversion takes place. So, through this simple example, we have, without going much into detail, in many situations these K r K T are computed, and first check we do two purpose. One is to check the whether the computational results are correct or not. The second thing, to find out how much energy loss is taking place by introducing a specific structure or certain structure. This is what here we are looking for. Now, in this this is the case of a deep water case. What will happen in case of shallow water? In case of shallow water, we have, if I just remind you the energy relation, the general energy relation, that is 1 minus K r square is C g 2 by C g 1 into K T square. And again, in case of a look at shallow water, in case of shallow water, this is L. In case of shallow water, C g 1 is root G h 1 and C g 2 is G h 2. Sorry, C g is C, rather C g is C, this is equal to C, this is also C. Then what will happen? Here also it will happen 1 minus K r square is H 2 by H 1 root over into K T square. So, this becomes an energy relation, and if H 1 is H 2, so at the far field I may have disturbances here, but if at far field, if this is my H 1, this is my H 2. So, local disturbances will not affect when it comes to energy relation. Let me put it here. Initially it was H 1, and then we have disturbances, and then it goes to H 2. So, if it is H 1 to H 2, then this relation will be occurring. So, what will happen in this case? H 2 is smaller. So, this quantity will be a quantity which is less than 1, and so in the process this relation will be satisfied, and that will give, and when H 1 is H 2, suppose that means I have whatever I have having in the beginning, maybe I have a structure here, or maybe I have a disturbances which is like this, where only if I consider only the wave reflection, but if it again goes to the water depth H 1 to water depth H 2, then the energy relations again remains 1 minus K r square is K T square. Here in case of deep water, it was just because water depth is, when we say deep water, the depth is after certain depth for K h is greater than 1, we call it a deep water waves. So, even if there is a variation in depth of when K h is much greater than 1, that will not affect this relation, but here in case of shallow water, this will not be affected only when this H 1 is H 2. The same relation will hold only when H 1 is H 2. If H 1 is not H 2, then this is the relation which will hold good. That is what in case of shallow water. And in case if we are looking from that wave propagating from shallow water, from deep water to shallow water, suppose the wave is propagating from deep water to shallow water. this is a abrupt change in the water depth, and then you will have again the same relation will hold 1 minus k r square is C g 1 C g 2 by C g 1 into k t square, and here we need to know what is C g 1 and what is C g 2. C g 1 the group velocity in this region on this side, and C g 2 is the group velocity on the other side, k t square. So, this is what I was interested to tell you, the wave transformation and the energy relation. Now, this in fact, this both in case of in case of a short wave or long wave, any wave, short or long wave of intermediate depths, any wave we think of, always the energy relation has to satisfy, and that is of this. So, this is one of the very important result, because in fact, we always try to validate our computational results, because there is one check that if this relation is satisfied, then we say that we are almost correct about our computation, and this is one of the best check or main check when it comes to a propagation problem, and this is what this is called the energy relation, and that is I was interested to tell you this. Now, another thing I will go to. Now, suppose I want to calculate one of the interesting problem is that when there is a abrupt wave transformation due to abrupt change in configuration. In geometric configuration of a bay or a channel. So, in fact, this is another interesting problem. In the what we have got, if we are going to this, let me just tell one more thing. What I am interested here, what I want to tell here is that here the interesting thing is that in case of a bay, in fact, we have seen that when k r square, in case of a wall, near a wall, we have seen that k r square is 1 or k r is 1, modulus k r, we have seen that it is 1, and in fact, when k r is 1, because we have 100% reflection, we have k r is 1, because here there is no wave, k t is 0, there is no wave which is transmitted. So, we have said that we can easily say in case of whether it is a finite depth, infinite depth, if we are dealing with a vertical wall, wave reflection by a vertical wall, whether it is a finite depth or infinite depth. So, k r square is always 1, and this is the energy relation in that case, because there is no k t here which is contributing, because our general relation is k r square plus k t square is equal to 1. So, this also holds good, and this is also a check that this also satisfies the energy relation. Now, what will happen? Now, suppose I look at a bay. If I look at a bay, it will have, or a channel, then I have two things. One is the bottom, there can be a variation in the depth, sorry. There is a variation in depth and breadth. Suppose I am considering that I will take a plan view. Suppose I have a channel of width B1, initially it was width B1 and it changes to width B2, and in that case, suppose this is the channel of width B1 and then it changes to width B2, and the depth of the water is, initially it was H1 and it changes to water depth H2, and I will say that this is same location, at the same location the changes takes place. Both depth and breadth changes from initially here breadth changes from B1 to B2 and depth changes. So, in that case how the energy relation? In that case the energy relation will change to, instead of I will use this as small b, that is better, I am using small letters. So, it will be EBCG is equal to constant. When there is abrupt change in depth, earlier I used to say that ECG, when I have one dimensional, there is only as considering one dimensional wave, here I am considering both breadth, ECG is a constant. But if there is no change in the, if the width does not change, if B remains the same throughout, only the depth changes, then I will have this also will be ECG is a constant. So, when we are considering a one dimensional channel, or even if a two dimensional channel we consider where the breadth plays an important role, then if the width remains the same throughout, then same ECG is constant, but if width changes from B1 to B1 to B2, then EBCG remains the constant. So, this is very important. Now, another interesting point, we know that we have to find 1 minus k r square is k t square, this relation it has to be satisfied, but at least one of the case will work out how to obtain k r and k t. We need to obtain k r and k t, and one of the way of obtaining k r k t is by direct application of the expansion formulae, that is Havelock's expansion formulae. The other way, because always it is not possible to obtain this k r k t in a direct manner, it depends on the geometrical structure of the structure by which the waves are scattered. So, if it is symmetric or very simple, then we can easily obtain it, otherwise it may be difficult to obtain the k r k t directly, and in such situation we may have to take the recourse of numerical methods or various numerical methods to obtain these things, and this is beyond the scope of this series of lectures or this course, that we will talk in detail later, because in this course my main objective is to introduce to some of the basic things about waves, and so I will not go to those details, that will come in a different course at all. However, I will try to illustrate this, that how k r k t can be obtained in some of the simple case, and basically I will concentrate tomorrow in my next lecture, that how, suppose I consider a simple case, water depth, change in water depth and change in water depth and change in width, how it affect, how in this case particularly I will consider in case of shallow water, the depth of water is shallow. In this case, even if we can utilize this energy relation, it will provide us one of the equation for determining k r k t without going to the solution, because and I will tomorrow we will in the next class we will see how this is helping us. This relation also helps us in obtaining the k r and k t, the reflection and transmission, because there should be some other relations which will help me. I should have two sets of relations which will give me that to obtain this k r and k t, and the detail I will talk in my next class, and there you will understand that how this is obtained. Particularly there are two things happens here. We have to always two ways we do this. Sometimes we consider the conservation of mass along with this conservation of energy equation, or sometimes we consider the continuity of pressure at the location where there is a abrupt changes in the geometry of the structure. By using one of these along with this, we can always find out how the energy, how the reflection and transmission coefficient changes. Particularly we can find what is k r and k t, and tomorrow I will talk about that, and then I will talk about the, instead of tomorrow I will rather say that in the next class, and then we will talk about how to general. I will briefly discuss about the wave load on structures, and once I discuss about wave load on structures, I will just discuss in brief about wave load on structure, and then we will conclude this part of the wave mechanics part of this marine hydrodynamics course. Perhaps I will not go to the nonlinear theory and the finite amplitude wave theory, which will be take much more time than it is expected. So, I will tomorrow I will talk about this wave load on the structure and a little about this, finish this part of this lecture and then conclude this wave mechanics part. And after that I will go to the details about a brief introduction about viscous fluid and laminar boundary layer theory. That will come in the next few lectures. With this today we will stop here. Thank you.